Hello, my name is Byungmin Kim from Triple IXR Lab. The paper I'll be discussing is titled Thinking from Limited Views, Understanding VLM's Spatial Mental Modeling Capability, which investigates the spatial mental modeling capability of vision language models and introduces the MindCube benchmark. This work has been accepted at ICLR 2026. To motivate this work, we first have to consider how humans perceive and represent three-dimensional space. When navigating an environment, humans observe it from a limited number of viewpoints. Despite this constraint, we are able to construct coherent internal representations of the full spatial layout, including objects that are no longer within our field of view. This cognitive capacity, termed the spatial mental model by Johnson Laird in 1980s, enables us to maintain object permanence, infer spatial relations among occluded entities, and predict the visual consequences of hypothetical movements. As illustrated in the figure, when transitioning from view 1 to view 2, certain objects such as the hand sanitizer become occluded. Nevertheless, humans readily infer its continued presence and relative position. This raises a fundamental question: do current vision language models possess an analogous capacity for spatial reasoning under partial observation? The empirical evidence suggests that they do not. Current VLMs exhibit three principal limitations. First, they are unable to reason about partially observed scenes. When objects are occluded or outside the field of view, the models fail to account for them. Second, they lack the ability to maintain spatial consistency across viewpoints, often producing contradictory spatial judgment from different perspectives. Third, they are incapable of performing spatial mental simulation, the counterfactual reasoning that enables humans to predict how spatial configurations would change under hypothetical transformations. These shortcomings highlight the need for specialized evaluation protocols that explicitly target these capabilities. Existing spatial reasoning benchmarks are insufficient in this regard, as they predominantly evaluate single-view comprehension or query only about directly visible objects. The authors identify three core capabilities that require assessment: reasoning under partial observation, cross-view spatial consistency, and spatial mental simulation of hidden relations. This motivates the central research question: how can we enable VLMs to form spatial mental models from limited viewpoints? The paper presents three principal contributions. First, the MindCube benchmark, comprising question-answer pairs derived from images, designed to systemically evaluate spatial reasoning under conditions of partial observation. Second, a systematic comparative analysis of three cognitive scaffolding strategies: view interpolation, cognitive maps, and free-form reasoning, examining their respective efficacy in supporting spatial mental model formation. Third, the map-then-reason training strategy, which integrates supervised fine-tuning with reinforcement learning to achieve an improvement. MindCube encompasses three distinct evaluation settings, each defined by a different camera movement pattern. In the rotation setting, the camera stays in place and rotates. The model must build a holistic understanding from incremental visibility shifts, like turning your head in a room. The among setting is the largest QA pairs. Here, views are captured around a central object with adjacent ones. The model needs to synthesize information across views where not all objects are simultaneously visible. The around setting involves moving around objects. The key challenge here is overcoming occlusion and maintaining object permanence as the viewpoint changes. The questions in MindCube are organized along a four-dimensional taxonomy. What if dynamics tests whether models can simulate movement, translation, rotation, sequences, and simultaneous events? Relation queries ask about spatial relationship between agents and objects. Perspective taking evaluates whether models can reason from their own viewpoint or adopt another object's perspective. And visual patterns distinguishes between linear and non-linear viewpoint changes. The critical design principle here is that questions are intentionally about currently invisible objects. This forces the model to truly reason about space rather than just describe what it can directly see. The authors evaluated 17 state-of-the-art VLMs on MindCube. The results are striking. Even the best performing models achieve accuracy only moderately above random guessing and remain far below human-level performance. Proprietary models show strength in certain subsets of tasks, but no single model performs consistently well across all settings. Moreover, models that were specifically designed for spatial reasoning show inconsistent performance and often fail to outperform general-purpose VLMs. The takeaway is clear. Current state-of-the-art VLMs remain fundamentally limited in spatial mental modeling. To address this gap, the authors investigate three data structures that act as cognitive scaffolds to approximate spatial mental models. The first is view interpolation, providing intermediate views. The second is the cognitive map, a bird's eye representation of object positions. The third is free-form reasoning, explicit reasoning chains describing spatial inference. This presents the detail of each scaffold from the dataset. For view interpolation, intermediate frames are extracted from recorded video between the original observation viewpoints. For the cognitive map, the two variants are differentiated by their information content. The plain cognitive map is a structured representation containing only object identifiers and their two-dimensional coordinates. It can be understood as a minimal top-down spatial sketch. The augmented cognitive map extends this representation with camera metadata, the position from which each view was captured, and the corresponding viewing direction. This provides additional context for relating observed visual content to the underlying spatial layout. For free-form reasoning, the model is expected to produce a structured verbal account of its spatial inference process. These three scaffolds are evaluated across three experimental paradigms: frozen VLM inference without any training, supervised fine-tuning, and reinforcement learning. The experimental design is structured along two axes: the input provided to the model and the output it is required to produce. The table enumerates the principal configurations. Raw QA serves as a baseline. The model receives raw views and a question, producing a direct answer. View interpolation augments the input with interpolated frames. The FFR configuration requires the model to generate free-form reasoning prior to answering. AuGCGMapIn provides the ground truth cognitive map as supplementary input, and the key configurations such as CGMap FFR out require the model to autonomously generate both a cognitive map and a reasoning chain. This is the result of frozen VLMs without any parameter updates. Adding interpolated views provides almost no improvement, suggesting that additional visual information alone does not significantly enhance spatial reasoning. Providing externally constructed cognitive maps as input actually degrades performance, indicating that the model struggles to effectively use externally supplied spatial structures. In contrast, scaffolds that require the model to actively generate reasoning structures, such as free-form reasoning or map generation, produce modest but consistent improvements. The key finding from this phase is that passive structural input is insufficient, while active reasoning processes provide measurable benefit even without fine-tuning. The effects of supervised fine-tuning are substantially more pronounced. Fine-tuning on QA pairs alone produces a large improvement over the frozen baseline. Adding reasoning supervision is a modest additional gain, while training the model to generate cognitive maps further improves structural representation quality. However, the most effective configuration is the joint setting, in which the model first generates a cognitive map and then performs reasoning over it. This joint approach produces a clear performance advantage compared to either reasoning alone or map generation alone. Interestingly, model trains solely to generate maps quickly learn to produce structurally accurate maps, yet their task accuracy soon plateaus. In contrast, models trained jointly for map generation and reasoning continue to improve, suggesting that the functional usefulness of the representation matters more than geometric precision. Given the success of SFT, a natural question arises: can reinforcement learning further refine the learned spatial representations? The authors employ the VAGEN framework with GRPO and evaluate three experimental conditions. The first condition trains the base model from scratch using only free-form reasoning rewards. The second also starts from scratch but incorporates cognitive map generation alongside reasoning. The third and most critical condition initializes from the best SFT checkpoint and applies RL as a subsequent optimization stage. This is the result of RL. Training reinforcement learning from scratch yields only modest gains, indicating that reward signals alone are insufficient to teach spatial abstraction effectively. However, when reinforcement learning is applied after supervised fine-tuning, performance improves substantially. This demonstrates that reinforcement learning is most effective when refining representations already learned through supervised training, allowing the model to surpass the performance ceiling observed after fine-tuning. So this is the summary of key insights. First, view interpolation provides minimal benefit. More visual information does not necessarily mean better spatial understanding. Second, self-generated representations outform externally supplied ones. Providing cognitive maps externally actually hurts. Model must generate their own. Third, joint training of map generation and reasoning is the most effective strategy. The synergy of map generation and reasoning is the largest performance gains. Fourth, reinforcement learning is effective primarily when initialized from supervised fine-tuning. From scratch RL is insufficient. SFT provides the prior, RL raises the ceiling. Last, more importantly, functional utility of representations matters more than geometric accuracy. Representation that better support reasoning leads to higher performance. Imperfect but reasoning useful maps achieve higher QA accuracy than perfect ones. To summarize, MindCube provides a dedicated benchmark for systemically evaluating spatial mental modeling in VLMs. The evaluation confirms that current VLMs struggle significantly with spatial reasoning from limited views. Training models to construct cognitive maps and reason over them, the map then reason strategy yields substantial improvements, ultimately reaching higher accuracy. These findings suggest that improving spatial reasoning in VLMs requires training them to autonomously construct and leverage internal structured spatial representations. Thank you for your attention.